about a modeling approach for failure analysis of composite materials. And some elements of this approach were applied in some industrial application for composite structures. The problems that will be considered are failure initiation criterion, damage evolution, nonlinear anisotropic elasticity, nonlinear shear, and strain rate dependency. Many theories were developed for analysis of composite materials, and once a group of researchers decided to make a competition between them, they conduct biaxial testing of composite materials and provided unidirectional data of composites for the analysis of these theories. This formulation is not perfect since the strengths cannot be defined only by means of monolayer properties, but anyway, this is a start step for the analysis. This is a list of ranking provided theories, and we were encouraged by the winner. This is Zinoviev theory. It was modified to reduce damage parameters. So we use only two. This is psi 1 is responsible for fiber failure, and psi 2 responsible for matrix failure. And this is the way how to reduce elastic constants and constitutive relation for damaged material. The idea how to define damage parameters are demonstrated on this figure. So if the elastic solution based on undamaged material is out of failure angle surface, we have to find a damage parameter to arrive back on a failure surface. In one direction, in fiber direction, we assume a brittle failure. So we have to check this for every stress component in transversal direction, in outer plane direction, and in shear in plane and outer plane. This idea is suitable for a minimum strength parameters of the material, which is commonly available, which can be provided by suppliers of the material, and it looks quite simple. But if we have some additional data, it can be applied to achieve more accurate results. This is a damage evolution diagrams in fiber direction. As I said, we assume brittle failure, and for other strain components, we assume a constant stress value after we achieve failure stress in this direction. Of course, we have drop this curve on some stress level if it is known, or if we have some extended data with exact behavior for the load and corresponding stress, it also can be applied. And this is a way how to define damage parameters. It can be determined using constitutive equations I showed previously. The only problem to find damage parameters correspond to load in transversal direction. After some transformation, we have a cubic equation for the damage parameters. This cubic equation, and we always have at least one railroad. This failure model was applied for the verification based on worldwide failure experimental data. As you can see, experimental data also has quite big scatter, because it's quite complex experiment for backside loading of composite material. And we do two types of the analysis to predict damage onset, and full failure of the specimen. In this case, the specimen was subjected to combined tension torque, and in this to tension compression and internal pressure. So in this part, the result was affected by buckling. So no theory can predict this, only based on stress. We have to model a full specimen size, and after some corrections, it match pretty good experimental curve. Another verification problem is open hole compression test. Here, nonlinear shear diagram was applied, dependency from shear stress. And if we compare with use of a constant shear modulus without application of that nonlinear diagram, the result is quite different of damage distribution to the thickness, since the shear stiffness drops if you have nonlinear diagram. And the loading diagram also changes if we apply nonlinear shear. This is another phenomena for demonstration of nonlinear behavior. This is off-axis test of the material to tensile and compression in different orientation. These diagrams are strongly nonlinear, and of course the linear elastic model is not sensitive to this. But the more evident effects is a difference in tension and compression, and as mentioned before, nonlinear shear behavior. To capture this effect, an anisotropic elasticity theory was applied. It based on introduction of triaxiality parameter to characterize stress depth. We formulate elastic potential, which depends from classical view, the way that the parameter has dependency from triaxiality parameter and also shear parameter. In case of this constitutive relation corresponding to that potential in the case of stress, plane stress. So the problem is to determine parameters that are not arbitrary, since we have to guarantee positive definiteness of elastic potential. And this is some further assumptions, linear form of these functions, and some assumptions for nonlinear shear. This is a demonstration of influence when we apply linear model and propose model for the problem of buckling prediction. As you can see, the deformations and buckling shapes are completely different, and of course it have to impact to failure analysis. And the final effect that I would like to consider is the strain rate dependency, and the idea how to capture it. The basic assumption is that strength function has dependency only from the damage parameter and the damage rate. So we can decompose this function into quasi-static and dynamic parts. And after we have an analogy with strain rate hardening, we have to determine functions using which agreement with experiments will be achieved. So here we used use analogy with plasticity and suppose such form of the function. And the final step is to determine constant. The idea is to use some trivial constants to solve ordinary differential equation and to try to achieve the best match of experiment. And the conclusion, I would like to say only about future efforts. This is to extend this model in 3D space with nonlinear elasticity and consider it in conjunction with the failure model. Thank you.
Thank you. Are there any questions?